Have you ever wondered why professional athletes earn so much money? One of the reasons is that they are insanely skilled. They can do things like this or like this. However, those very tricky ball movements are based on a well-known effect, the Magnus effect. Applied to sports, Magnus effect is the propensity of a ball that is moving and rotating to deviate perpendicularly from its initially intended trajectory. For example, seen from the side, if a ball is traveling in a straight trajectory from left to right, rotating clockwise, its interaction with the air will develop a perpendicular force to the free stream flow direction that will push downwards in the y direction. To show the Magnus effect, we have developed a series of experiments using cylinders and conventional things, so, with precaution, anybody could reproduce them at home. As can be seen in the equation, the force per unit length acting on a cylinder depends on the radius of the cylinder, the rotational speed, the density of the fluid, and the velocity of the fluid. Here, we can see that with a rotation, the cylinder simply drops. However, when it is rotating, a change in the trajectory is clearly visible. For the second experiments, a longer cylinder was used. As expected, the longer cylinder develops a greater force and the landing point is different than before. In another experiment, we changed the radius of the cylinders. However, the equation to calculate the Magnus force was developed for an inviscid fluid. In this case, with real fluids, viscosity cannot be neglected. Many things are happening in this experiment. A smaller radius means a lower weight and also lower drag force, since the surface area is smaller. So, despite having a smaller radius that could mean a smaller force, the combined effects of all the changes resulted in a greater deviation from the original landing point. Finally, we also changed the fluid and used liquid laundry detergent that has higher viscosity than water. In this experiment, the viscous effects are very clear. At the beginning, a greater force is developed, but the friction is so big that it slows down the rotation of the cylinder until it stops. For this reason, without rotation, the cylinder simply drops, and the landing point is closer.
Now, no sails, but instead of that we've got these three rotors, 20 meters high, and they're going to spin, which gives you a thrust vastly more than a sail would do.
The Flettner rotor was originally invented by Anton Flettner, a German engineer in the 1920s. The rotor spins round at high speed, performing the same function as sails, but 15 times more powerful, providing the forward thrust to drag a huge propeller through the water.